Alright, thanks for watching, and today I will do one of my favorite multivariable calculus problems because you'll see it's very soothing. It's like math. It's a math chillax session if you want. Namely, we will find the average value of this function, so 1 over square root of x squared plus y squared, over the following ring. Because if you like it, then you should have put a ring on it. Okay, and by the way, here ring as an annulus, not as an algebraic ring. This is not an algebra class, okay? So it's the ring, x squared plus y squared, it's squeezed between a squared and b squared. In other words, the region between two disks, one of radius a and the other one of radius b. Or in intro calculus, they call it a washer, but it's really a ring. So you kind of want to find the average value of this function, which if you want it blows up at 0 and it goes down to 0 very quickly, and you sort of want to find the average value over this ring, sort of in this profile view. And you'll see the answer is very, very neat, but let me remind you how to find average values of functions in 2 dimensions. So it's very similar to the formula in 1 dimensions. Remember, in 1 dimensions, the average value of a function is the integral of that function divided by some number, which is the length of the interval from a to b. In this case, the average value, it's still an integral, but this time it's a double integral. So double integral over r of f of xy dx dy divided by some number, which in this case becomes the area of the ring. And by the way, this makes sense in terms of average values. An average value, what is that? It's the sum of all the values divided by the number of values, which in this case, well, an integral is just a sum, and the number of values in this case is the area of our region. And so first of all, let's just get rid of this area. So the area of this ring, and I'd like to remind you, our ring is just, the region between two disks. So this is A and this is B. And so because the ring is the region between two disks, the area is just the difference of the areas. The area of the ring is the difference of the areas of the circles, which in this case becomes pi b squared minus pi a squared, which if you want, it's pi times b squared minus a squared. And just for later purposes, let's just factor it out as pi times b minus a and b plus a. Okay, that wasn't too bad. Okay, so that's the area of the ring. And now let's just calculate the double integral. And you'll see that's the exciting part. So the double integral over this ring of f, which is 1 over square root of x squared plus y squared dx dy. So you see x squared plus y squared, again, it's assigned to use polar coordinates. And moreover, the nice thing is this ring itself can be conveniently described in terms of polar coordinates. Because notice, what we have is the radius in terms of polar coordinates is actually squeezed between A and B. And moreover, the angle, theta, well, it's everything. It goes from 0 to 2 pi. And therefore, this whole integral becomes integral from 0 to 2 pi, integral from A to B of 1 over square root of x squared plus y squared. Just becomes square root of r squared, and then dr d theta, except do not forget about this extra factor of r, because har d har har, okay? And then this becomes integral from 0 to 2 pi, integral from a to b, 1 over r dr d theta. And notice, this is why I really like this problem, the r's, they cancel out, and then you're just left with the integral from 0 to 2 pi and from a to b of 1 dr d theta. But then integral of 1 dr, it's b minus a, and if you integrate that with respect to theta, it becomes 2 pi minus 0. So in the end, this becomes 2 pi times b minus a. So the integral itself, it's 2 pi times b minus a, and I'd like to remind you that the area of our region was pi times b minus a times b plus a. And so our answer is just a quotient of this. So 2 pi times b minus a over pi times b minus a times b plus a. And there's a beautiful simplification here. So not only the pi simplify, but also the b minus a. And you're left with 2 divided by b minus a. And let's actually write this in more suggestive notation. So it becomes, if you want, 2 over a plus b. And that's really 1 over a plus b over 2. In other words, the average value of this function over the ring is just 1 over the average value, let's write it x bar, of the radii of the rings. So, in other words, let me illustrate this. So you have those two rings, one of radius a and one over radius b. Then the average value is in the middle. And the value of the integral, the average value of this function is 1 over x bar. And the nice thing is, this integral, this average value, only depends on the average value of a and b. So in other words, it doesn't really depend on the values of a and b, just on the average values, which means that even if, a is very close and b is very far, as long as the average value is the same, so you could also have a and b be here, as long as the average value is the same, the average value in the end is the same. And which I think illustrates this nice property of 1 over square root of x squared plus y squared, which we didn't know from before. So and that's why I think double integrals are kind of useful in this sense. Alright, so I hope you liked this math relaxation session. If you want to see more math and more integrals, please make sure to subscribe to my channel. Thank you very much.